Busters. What should we do today?
Let's go flower viewing.
Yay!
Yeah. Hey guy, what I found.
A flower.
Oh, why is it here?
It looks like the Chemiluminati's been here.
Let's look at the flower under a UV light.
It's glowing. Why?
The veins, they're glowing.
Let's compare this to another flower.
It's normal. This all points to the handiwork of Dr. Luminescence. Be very careful, guys. This guy's dangerous.
Welcome to my evil lair. It's a bit dark in here. Maybe you could use the light.
What evil, dastardly deeds are you doing, Dr. Luminescence?
Well, you see, I've cut open a highlighter and used the ink pad. With some water, I've concocted a solution that will make the world glow. When I spread this fluorescent solution, I will use the sun's UV rays to make everyone glow forever.
Wait, what about the flower?
You see, my little glowbusters, the flower was only a test run. It was to see if an organism could absorb the solution and eventually begin to glow.
Quick, grab the bottles. We must escape while we can.
What are you doing? Is that what Dr. Luminescence talked about?
Yes, he would take the fluorescent ink out of a highlighter, and then he would empty it into water to create a solution that would make the world glow. Fluorescent ink. I will now repeat this process. That was very explosive. Don't try this at home. Ink seems to come out at the other end.
It's a lot of ink.
Yes, this is very concentrated. He must dilute it to get so much. What dastardly plans has he for the world? I think this should be enough.
And now you'll go fill it up with water?
Yes. I seem to have stained myself with his fluorescent solution.
It's non-toxic.
So it must be okay. But he still plans to make the world glow.
Yeah, that's pretty bad.
Dr. Luminescence, we found out how you do it.
Oh, did you now? Then why don't you explain it to me?
As you can see, the reason why this solution glows is based on a property called fluorescence, in which something like this absorbs short wavelengths, short high energy wavelengths such as UV light, and re-emits that excess energy as longer wavelengths, such as the yellow presented here. However, on the atomic level, what happens is that as the atom absorbs the UV rays, or the high energy wavelengths, the electrons, they jump to higher excited state. They jump to a higher excited state, and when they go back to their ground state, the energy that they absorbed is then released in the form of protons, and as I said before, longer wavelengths that are shorter energy than the UV rays.
Then pray tell, why do I favor the yellow solution over the blue?
We hypothesized that maybe it depends on the visible light spectrum. Because ultraviolet light contains such short wavelengths and is much far into the electromagnetic spectrum, the visible light spectrum is dependent upon the fact that the colors in there all have much longer wavelengths compared to ultraviolet. For example, blue or violet, as presented here, does not glow as much because the wavelengths are much closer to ultraviolet, therefore having much shorter wavelengths and much closer to the energy levels of ultraviolet, and so the energy emitted when the electrons go back to their ground state and release the energy as photons, the glow is not as present. As compared to yellow, which has a much longer wavelength, the energy difference is so great that the energy emitted is enough to make it glow in the dark under UV rays.
Oh, but I think it also depends on the compounds as well.
Well, then you
But
proved
you
our
were right.
hypothesis wrong.
But you were right about the fluorescence. Yellow creates a stronger glow. Oh, but you cannot defeat me, for I have the power of my glowing Lepis Carpeums. Gah!
Ah! It's too strong!
Run!
Dun 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 dun.
Man, that fluorescent bunny was just too bright, too strong.
Actually, it was a bioluminescent bunny.
Yeah, bioluminescence is a form of chemiluminescence. It's what happens in anglerfish, how they produce their red light.
Whoa. Let's ask our scientific consultant, Jerry.
You see, my fellow glowbusters, bioluminescence is a form of chemiluminescence, where a reaction occurs that produces light. This occurs in several organisms, such as the anglerfish or fireflies. These reactions include luciferin, which is a light-producing compound. It reacts with oxygen, with luciferase as the catalyst. The light release depends on how the luciferin is arranged. In some organisms, photoprotein is used instead of luciferase, but photoprotein requires an ion to work, such as calcium ions.
Also, don't forget an electron pathway. An electron pathway is the mechanism used to transfer electrons when two light reaction happens and electrons need to be transferred from water to carbon dioxide.
But how are we going to defeat Dr. Luminescence?
Let me think. I got it! Glow sticks.
How do they work?
Chemiluminescence is the emission of light through a chemical reaction. This reaction starts with two reactants, reactant A and reactant B. These two react to form an excited intermediate. This intermediate is basically a chemical product in an excited state, meaning that the electrons in a molecule of this product are not at ground state. They have some excess energy that they have to release. These electrons release that excess energy in the form of light. The color of that light given off depends on the wavelength emitted.
Yeah, I get that. But how do glow sticks work?
Oh, you wanted to know about how glow sticks work. Well, it's the same principle, really. A glow stick contains two chemicals, diphenyl oxalate and dye. The glow sticks also have a glass vial which contains hydrogen peroxide. When we bend a glow stick, the glass vial breaks and hydrogen peroxide is released. This hydrogen peroxide reacts with the diphenyl oxalate to produce phenol and the cyclic peroxide. The cyclic peroxide reacts with the dye molecule to produce two carbon dioxide molecules, and in the process, the dye molecule becomes excited, meaning the electrons have jumped to a higher energy level. In order to get rid of this excess energy, just like in normal chemiluminescence, the electrons in the dye molecule release energy in the form of light, and therefore the glow stick glows, just like over here.
In that case, let's use these glow sticks and defeat Dr. Luminescence.
That's a good idea.
Wait, guys, they're not bright enough. We need to make them brighter to defeat Dr. Luminescence.
That's right. I heard that temperature affects the reaction inside these glow sticks.
That's right, because temperature affects reaction rates. by adding more energy with the heat, we're making the reaction rate go higher. And by doing that, we're making more products and more light. But that also means it's going to run out faster. So we have to be fast about defeating Dr. Luminescence.
That's true, and that means in the converse effect, by putting it in the freezer, what will most likely happen is that the reaction rate will lower, therefore, less product is produced at a much lower rate.
Let's go test it out. We'll put the glow stick in hot water. We'll put one in the freezer.
The hot water made this glow stick brighter, and the freezer made this one darker. Sorry, dimmer. Now, this stick is bright enough for us to defeat Dr. Luminescence.
Alright, it's time to go home. The Glowbusters.
Dr. Luminescence, we have come to defeat you and foil your dastardly plan.
Now face the wrath of my rabbits.
Your powers have no effect on us, Dr. Luminescence.
What? It didn't work.
Let's finish him, guys.
Oh! Not the power of chemiluminescence. Ah!
Mission accomplished. Glow busted.